Okay, so let's see if we can do a standard deviation by hand. And also, after we get it calc, let's take a little bit of time and kind of try to make sure we sort of understand, wait, what did this do again? What did this tell me? Let's see. So let's come up with something. Okay, so here's your data. Let's try to keep this reasonably small. Let's just do this with, say, 5 numbers. So I'll just make these up randomly. I won't have any particular purpose in these. Maybe those are percentages of somebody's grade or whatever. So you have these 5 numbers. Let me see, do I have? Do I have a copy of the note sheet for this? I do. Unbelievable. So you should be staring at this. Import. And have this note sheet kind of out and with you a lot, just because this, you will have this, as I said yesterday, on the test. So you want to be able to kind of, you know, it needs to speak to you, so to speak. So we're going to do a population standard deviation, the one that has the order of operations sort of built in from yesterday. So the question is, can you do that with these 5 data points? I'd like you to see, I'd like you to sort of get ahead of me here. Do this on scratch paper. So in order to do this, what's the first thing you got to figure out about this? You can't just start doing the standard deviation. What do you got to know right off the bat? The mean. You got to figure the mean out right off the bat. Remember, this is the symbol for that. Well, it's the symbol for the sample mean. And so we have these 5 numbers. And I just made these up, so I don't know the answers to this either. Now, just an interesting side note, because again, I want you to pay attention to this. So I just quickly typed this in and I got 45. Why should I not accept that? That's what's on my computer. That's what's on my calculator right now, 45. That's smaller than every single number up there. Can that possibly be the middle number? You see what I'm saying? Now, in my case, thanks to, the calculator shows everything. One of my plus signs is a division sign, so it's like, oh, I'm stupid. Like, you're going to make that same kind of mistake. Now, in my case, I got kind of lucky because my mistake was so profound that it was actually obviously wrong. If that number had come out like 79 or something, I would have thought, oh yeah, that's in the middle. That's probably right. So I go back and fix it. And I got what I think was it Tisha that said that. This time I got 78.2. Again, that still might be wrong, but at least that looks reasonable now. And notice I used an equal sign because when I divided by 5, it actually wasn't a decimal that went on forever, so I didn't have to round it off, which is kind of cool. So this is actually perfect. That's the perfect mean. And so now you start stepping through the process. I mean, let's reiterate. And you gotta write a lot of stuff down here. Like, you can't just punch buttons and have the answer to this pop out. You gotta write a lot of stuff down. So What's your first move here? What's that? What's that saying? What's your second move? What's your third move? What's your first move you got to do? Yeah, you got to take each value for x, like x1 and then x2 and then x3, like each of those individual numbers one at a time, every single one of them. And you got to subtract the mean from it that we just calculated. So I'm gonna have to write all those down. Does that make sense? I mean, I kind of don't have a choice but to write all those down. And then my second move is going to be to square each of those answers. And again, that should make sense to you because the order of operations is parentheses first, exponent second. So you should find yourself saying, I actually really don't need your little cheat sheet there. I got that. However, this one is a little weirder, but basically this one is because this giant division sign means you have to finish what's on top. And again, you don't have to memorize this. I look at that symbol that's brand new to you and it says, oh, that means sum at the bottom of your note sheet. So that's kind of a fancy way of saying add all those numbers that you just squared. They're going to be really big numbers. Add them all up. And then finally, or close to finally, divide by n. And then last, take the square root of that answer. So looking at your note sheet, I'm going to give you a second. Can you do that? Now, I would recommend, especially because you're as inclined to make dumb mistakes as I just made, yet again, like show me some of this, because I am going to ask you to do this by hand on a test. And if you make a dumb mistake and I can determine it was just an accident, then I can still give you most of the points. So, you know, tell me some of this stuff. Write this stuff down. So I'm going to make kind of an organized list here. This is my x minus x bars. I don't really have to write anything else down. So I'm, you know, just starting into it. And then kind of once I do that, then I'm going to need my x minus x bars. I'm going to need that squared. So I'm going to kind of have a list of, you know, 5 numbers here and 5 numbers here so that, you know, if you do push a button wrong, I can go, oh, they got 4 of them right and one of them was wrong. So they obviously know what they're doing. They must have just hit a button wrong. I do that all the time. I won't take very many points off, but you got to take me on the journey a little bit. So you get ahead of me. And I'm gonna walk around. I don't know the answer to this because I just made this up, but I want you to get it by hand. And then the second thing we're going to do is use the graphing calculator. I'm going to show you how to get it to sheet, tell you the answer, like you do nothing. Just type those 5 numbers in, bang, and that pops the answer. And you should do the same thing we're doing by doing it by hand.
Yeah, that's one of those. I'm not really sure.
So would you agree with these numbers right here? Deviation? That's why we subtracted each of those values. But the average, that's not quite as much. These are the deviations. So
But I'm trying to like, and after the flow,
that's kind of in the middle.
they're looking at the- So that's where I was like,
Because we're looking for the, not the average of the number, but the average of the deviation. So just like this would be the deviation. I would agree. There's one less, there's one less, there's one. So I'm going to catch up to you now.
How do you feel about us writing our own notes on the note paper or is that like not allowed?
A little louder, what?
How do you feel about us writing our own little notes on the next note?
Yeah, it's a good question. Let's talk because if it's good for you, I want everybody to be like, hey, that's a good idea. Let's all steal it. I mean, I guess I would say, like, I wouldn't want this example to be sort of written on the back. But I don't know, that's debatable. I gotta think about that. Show me what you have in mind and let's talk about it. So this is not hard, but it would be easy to push a button wrong here. This is very important.
I have a question.
Please.
So, yesterday you were saying that like the reason that you square and you then do the square root is to like get rid of the negatives. Like why doesn't it work just to, I mean, I know it gives you a different answer, but why doesn't it just work to like average the actual deviation itself?
Yeah.
Without the negatives.
Yeah, and honestly, I've investigated that a little bit. And I can't figure that out. In other words, what Tisha's asking is, these are the deviations. In other words, this tells you how far each of these people were from the average. So the average of the group was 78.2. This person's very happy. I keep forgetting I gotta turn that on. This person's very happy because they're 20 points above average because it's positive, right? So if these are like test scores, that makes that person really happy. Hey, I got 20 points more than the average. I did really good on this test. This person is not as happy because they're 13 points below the average, right? And so people are above, people are below. They're all over the place. A common sense understanding of standard or typical deviation is to do exactly what we did the other day and exactly what Tisha just said, which is if you just got rid of the negative signs here, because deviation, if we decide, okay, what's the average deviation, and we don't care whether it was up or down, then just make all these positive, add them up and divide by 5, take the average deviation. That is what a standard deviation is, but oddly, it isn't the same answer as we get when we square and square root, because squaring and square rooting gets rid of the negative sign. My only guess at this, and what I've looked at a little bit, is computers, I guess maybe when they were first sort of, like, technology wasn't very good at finding an absolute value. Does it make sense if you add up these deviations and you add the positives and negatives, you're actually going to get 0 for that. When you add them up, all up, you'll get 0. So you actually have to change all the signs. I'm just wondering if, originally and I actually don't think this is the right answer, by the way, but I'm thinking originally technology, maybe it was easier to get a machine to square something and square root it. And so you get about the same answer, but you actually oddly don't get the same answer. So conceptually, it'd be way easier just to add these up as positive numbers, divide by 5. That's the average deviation. So there is average deviation and standard deviation are actually slightly different, two slightly different things. But this produces a slightly different answer. So yeah, ultimately, I don't know the answer to that question. Now, so to save time, I'm going to go back and square each of these numbers. But remember, as I said yesterday, you got to be a little bit careful squaring the negatives. So I'm just going to type 13.2 and square it. I'm not going to type negative 13.2 because I already know it's positive. And again, I'm punching a lot of buttons here. The chances that I do something wrong are pretty high. I often sort of jokingly say when I'm teaching, like, I never make mistakes when I teach. And the reason is because there's always like 20 people staring at every single thing I write down. And if I get it wrong, somebody always raises their hand and fixes it, right? Like you don't have that luxury, you're all by yourself. One thing I would recommend though is just, on a test, like rather than rush through it, like stare at it. I just tried to type 10.2. Hey, look, I did. Like check that. Don't just quickly rush through it. But do you understand what I'm saying? In other words, if I look at your list and that one's wrong, but the other 4 are right, does it make sense? I know you know what you're doing, but something just spazzed out right there. So now we're almost home free. So our next step in the order of operations was to add all of those numbers together, right? And I wouldn't expect to see anything here except for the answer to this. So I'm hopefully, again, typing all of this again incorrectly. But in a second, when I show you how to get the graphing calculator to do this too, then we'll be able to check our own work. Like you don't have to check with somebody else, just get the calculator to tell you the answer way more easy. So I added this and I didn't really check my work very carefully and I got 826.8. Does it make sense if on a test I say show your work? I should see all of that. And now I'm almost home free. I just have to take that number and divide by what?
5.
Divide by 5. But I do want to point out, because I'm sure this will come up on your assignment, there's a difference between population standard deviation, which is that symbol, and sample standard deviation, which is S for sample. And again, do you notice the difference? What would we be dividing by right now if this was a sample standard deviation?
I was going to interject about that. On the
4.
sorry,
Go ahead.
on the homework, it had a question that said, where's the standard deviation? And it just said standard deviation.
Right.
And it didn't say population.
Didn't say which one.
So I did the population, but that was wrong, and then I did the sample, and that was right.
Yeah, and actually I'd like to know that because I can actually go into the structure of these questions if I didn't catch that in a previous class. If you send me an email, first of all, little things are going to go wrong in your homework assignment, and you do get 3 tries to fix stuff like that. And notice you were sort of able to solve that yourself. However, if I had only gave you 1 try, then you would have got it wrong, and that'd be really frustrating because you totally understand what you're doing. So number 1, you can always send me an email like, hey, I got this wrong because I was off by 1 decimal point. I'm going to give you those points. Now you should still learn from it. The reason you got it wrong is you rounded too soon. But that's not wrong if you missed it by 1 decimal point. So I'll go in there and add the points. Secondly, that particular question that you're talking about, that should have said sample because there's 2 formulas for this. If they didn't say that, that's not really fair. I can go into the code and actually change that for the sake of this class and future classes. So I actually want to fix that stuff. So that kind of happened here, didn't it? Like I just said, find the standard deviation, and we really talked about which one we're doing. I was pointing at the population one, so I'm going to continue with that one. But I will just quickly write down the other one just so you know. So I take that number, I divide by 5 on my calculator, and then I get 165.36. And finally, I take the square root of that, and I get, and again, notice you have a rounding. You got a crazy decimal for this. Notice the symbol I'm using, and notice I'm using an approximately equal to sign. And on a test, I'm not going to say anything about rounding because I really don't care. However, there is kind of a standard to this in statistics that maybe it'd be nice to know. But notice what kind of data did we have? Discrete or whole numbers. And so it's when you make a calculation, it's actually kind of common to round it 1 more decimal place. So since I got 12.859, I would call that 12.9. But I don't care. Did you call it 12.86? Good for you. Did you call it 12.859? Good for you. Did you call it 12.8592? Good for you. Like, who cares? You got the answer. But I would like you to stop and stare at this for a second, because again, a minute ago when I got 45 right here, I immediately knew something was wrong. Can you stare at this? And I had a chance to talk to 2 of you about this. Can you stare at this number and go, yeah, it looks about right? Remember, these were the deviations, right? And this is supposed to be the average of the deviations. That's what standard deviation means. So look at them. 8, 13.2, 6.2, 20.8, 10.2. Is that number like in the middle of those? Does it look like the average of those? Notice it does. Now, it doesn't mean I didn't make a mistake, but it's like, yeah, 20 is big. 13.2 is big. They're on the high side of this, but then 8.8, 6.2, and 10.2 are all below it. That number really does look like it's in the middle. It does look like the average of the deviations. So on average, so sort of the big takeaways for this when we're sort of all finished is to say, all right, I had all these data points. And remember, you wouldn't really need to do these calculations if you only had 5 numbers. You can just stare at 5 numbers and kind of see what's going on, right? So we're sort of pretending this came from 500 numbers. So we're saying, yeah, the average on that test that I gave was 78.2, and it wasn't weird. It was actually very typical for people to deviate from that by 12.9. So I'm just going to write this down. Like, remember how the sample you'd be dividing by 4? If I took 826.8 divided by 4, got an answer and square rooted it. I'm going to erase this, but if that's the case, I would have got the sample standard deviation is 14.4. I just want you to have a sense of like, why did somebody make this formula what it is? Notice this is larger. When you divided by 4, that actually made it larger. And that makes sense. If you had a certain amount of money and you divided by 5 people, don't you get less money? If you divide by 4 people, then you get more money, right? So this number is larger. And so the reason for that is if you're doing a sample standard deviation, does that make sense? You didn't check everybody. So if this is just a sample of 5 people that, you know, it's like 20 people took the test and I took a sample of 5 of them, does it make sense? There could be some people that got really low scores that weren't on the list or really high scores, and they would have caused more deviation. So because there's a chance that the deviation is worse, since I only checked the sample, you're sort of arbitrarily bumping this up a little bit larger to kind of account for that. That's the idea. But notice it's not way different. It's not like it's 27 or something. I mean, it's just a hair bigger than the other one. And also, by the way, if n, in this case, n was 5, if n was a really large number, like 112 points of data, does it make sense if you divide it by 112 or 113? Those numbers are so close to each other that almost you wouldn't even see a difference. So interestingly, the larger the data set is, the less the difference is. So just so you have some logic, but you do have to pay attention to the note sheet because there is one formula for a sample and one for population. In the real world, sample is the one you actually do most of the time because you can't, very seldom can collect all of the data. Does that make sense? You have to do a sample. Now, to make sure that you understand what this means, what does this mean? I said this a little bit yesterday, but we'll go into that now. This means that if I take X bar plus or minus 1 of those standard deviations, in other words, we said it was typical to deviate by 12.9, either up or down. Notice we're not saying what direction that 12.9 is. So I'm going to take 78.2 plus 12.9. And I get 91.1. And if I take 78.2 minus 12.9, I get 65.3. You understand what that range is getting at right there? That's saying that although I've lost the original scores, or there were 500 numbers and I couldn't stare at them all because it just overwhelmed me, this is basically saying that most people hung out right there. So the scores were kind of in there, a large majority of them. Now look at the scores. You can see them up here. There's not that many. Were all of them in that range? Notice there was one that was a hair too low and one that was pretty high, but the other 3 were actually in that range. So that's what it's saying. It's saying like most people hang out in that range right there. As I mentioned yesterday, though, that doesn't capture everybody. So it's not weird to even go 2 standard deviations above and below. So now if I go back and say 78.2 plus 2, I'll write this down, 78.2 plus 2 of those 12.9s. Again, do you see the formulas we've been doing lately? I mean, that's the formula. I take the mean plus 2 standard deviations. Like, that's an algebra formula. If I do that, I get 104 for the top end. Exactly. If I didn't type that in wrong. If I subtract, because it's plus or minus, I get 52.4 for the low end. That's my range. Did that capture everybody? Does that include, did that range include every person that took my test, so to speak? Notice it did this time. That captured these sort of last 2 people up here that the first didn't capture. So that turns out to be the practical side of this. If you go in for a medical test and you are outside 2 standard deviations from the mean, that's considered unusual. That's a very important idea. It's going to follow us the rest of the term. This is kind of a charged word. That's unusual to be outside that. Now, if this is a test, does it make sense you can't be unusually high? You can't get over 104%, so it's like impossible to go that high. But if you got below 52.4, then you were unusually low. Now, again, unusually low in what sense? Well, relative to the other people. Like, there's not a right answer to what your body temperature should be, but if you're 2 standard deviations higher than other people, your temperature is unusually high. If you're 2 standard deviations below other people, your temperature is unusually low. There's not a right answer to that. That's just you being compared to other people. There's not a math equation that says what a human body temperature should be. So we just have to do statistics to kind of figure out what it is. And then we use plus or minus 2 standard deviations to decide, should we have you, get tested, start taking medication. So my cholesterol was more than 2 standard deviations above the mean. And that's why the doctor said, all right, start taking this medication, start doing stuff different. You see the practical side of this? You see why this is kind of a neat thing? If it wasn't for what I just did there at the end, then this would just be nerds being curious about the world, right? Now, I want to show you how to get the calculator to get 12.9, and it's exactly the same answer. But in our world, anytime people plug stuff into a formula, someone has made an app, someone has made a computer program, computer app of some kind, because not everybody knows algebra. And also, if you're actually using algebra that affects people's lives, you can't afford to get it wrong. If you're going to give someone medication, let's not screw that up. I'm designing house plans on the side. I'm designing a beam for someone's house, and I can't be wrong. That's not an option. So I put all the numbers into a computer program and it pops the answer out, and that sort of guarantees I don't do something dumb, even if I know what I'm talking about. Okay, you ready? So there's our numbers. Zoom out a little bit. Man, this is like Galera City. You probably have the numbers written down, so I can probably forego the. Okay, now in my open math, I have at the bottom of the list of stuff in there, there's videos, there's calculator videos. So what I'm showing you here is you can watch it again yourself in slow motion. But I would also, for now, interrupt me. Oh, wait a second, what'd you just do right there? I want you to know how to do this. But there's some steps to it. Okay, so we're gonna go here a lot. Take a look where I'm pointing. It says stat. That actually kind of makes sense, doesn't it? You're in a stat class, you're in a statistics class. So hit stat. You have 2 things that we're gonna do in this class. We're gonna be in every one of these buttons right here before this class is over with. And we're not gonna use everything that you see here, but we're gonna use a number of those things. But for right now, to start off with, I can edit and I can calculate. Well, I want to edit because I don't have the data is not in there yet. Does that make sense? So right now, edit is highlighted, and so I hit enter. And notice when you go there, there's probably nothing, but you see I have numbers sitting in list 1 and list 2. Well, that's because I'm a nerd and I've been in here before. You probably don't. Now watch this. So those are kind of in my way. Does that make sense? Now you have one choice is right here. It says delete. So I can hit delete, 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 and finally they're gone. The other option is, remember when I was in stat a second ago? Notice how down here there's another option that says clear list. This is like erase the whole list. Delete's probably easier. It didn't take that long, right? I'm never going to have you enter like 60 numbers in there, so you have to hit delete all day. But I could go in and hit clear list, and basically now it's blinking saying which list would you like to clear. Now in my case, I know a second ago it was list 2. And notice right down here, it says list 1, list 2, list 3, list 4, list 5, list 6. How do I get list 1 to happen? Yeah, see that second is blue for me. So I got to hit second, and mine was in list 2. So I hit list 2, that's the one I want to clear, and it says, okay, I'm done, I did it. And sure enough, if I go to stat and I go back to edit, look at that, it's gone. So, you know, you got leftover data in there. You're going to have that a lot in this class. So you got to get rid of it somehow. So now, easy. All you do is type it in. 87, enter. And you can also hit the up and down arrow keys right here. But 87, enter. 65, enter. 72, enter. 99, enter. 68, enter. All my data is in there now. Now, one of the huge dangers of this, because this first test, I want you to show me now how to do this by hand. But after this, we're never doing it by hand again. So you better make sure you type those numbers in right on all tests after this, because everything you do is going to be wrong if you don't have them typed in right. Take 2 seconds and stare at those numbers. Make sure that was the numbers that are on the problem on the assignment or the problem on the test, and so that you didn't get them wrong. Okay. Good. Now, does it make sense? I burrowed way into the middle of this calculator, and I'm in stat, and I'm in edit, and I'm editing this data. Well, like, what if you decided, okay, I'm done with this, and I want to like add 2 + 2 again. I want this just to be a normal calculator. So like, how do I get out of here? So one cool thing is you don't have to save that. Anything you type in just automatically is saved in here. But you do got to get out of here a lot. And see right above mode, it says quit. That's how you get out of this. We're in stat edit mode. And anytime you're like, I want out of here, second, quit. Now it's a calculator again. If I want to go 6 times 9, bam, it's a calculator again. So I got out of there, quit. You can always hit clear right there to kind of erase the screen as well. But remember, this I'm assuming you've just got this calculator out of the box. You've never had a class before that needed this machine. So this should feel pretty unfamiliar to you. Watching me do it once does not equal you now understand it. Okay, what do we do? Well, now we go back to stat again, except for we don't want to edit this time. We want to do something different. So I'm hitting stat. Just out of curiosity, notice there's some things that are kind of cool. What do you think sort A and sort D would do? What do you think the A and the D are? You might remember this from Excel. A is ascending and D is descending. Like if you wanted to sort those in order from smallest to largest or biggest to small, whatever, it's like you could do that. You never need to do that, but it's just interesting. All right, arrow over to calculate. So again, I can use these arrow buttons right here to go up and down. And fortunately, I want the very top one. I want one variable statistics. Does it make sense? I just have one variable test score. I have one variable. So I hit enter. Notice mine says list 1 there. In other words, it's saying I'm about to do this to list 1. Does it make sense if that doesn't match where my data is? It's not going to like that. Some of your calculators, if you got it from the library, like there might not have been a list 1. You can actually delete that, and the lists can be kind of screwed up. So don't do anything, but I'm going to go in here and change this to list 2. And if I say calculate, of course it says error because there was no numbers in there, right? So it's like you just asked me to do statistics, and there isn't any numbers in there. And so it gives me this weird message like, what are you doing, dude? So stat, calculate, one variable, statistics. This is supposed to be list one. So if your numbers are in list 3 and you made that list 3, then it'll work. So I'm just arrowing down to calculate, and I say calculate. And you should see some things you recognize there now. Now what this did is it gave you everything. And even some stuff at the bottom. Do you see how there's an arrow right there at the bottom? There's even more. And that's something we're going to be studying in a couple of days. And so this actually gave you everything that you need to know about that list of numbers. Also, notice the symbols. Look at that very top one. Do you see how you got to know some statistics to even read this? Before this class, if I said, hey, X bar is 78.2, you'd be like, what the heck is that? But it's like, I didn't make that up. Like, that's a universal symbol for the average. And so notice it found the average automatically. I didn't have to add them up and divide by 5. And then what do you notice about these two numbers right here and these two symbols? S for standard. There's the sample standard deviation that I wrote on the screen a minute ago. And there's the exact answer that you got for the population standard deviation. And isn't that cool that we didn't have to do one thing? Like, we didn't have to know the formula. We didn't have to write all that chunk down. It's just bam, there's the answer. Nobody does what we just did by hand in the real world. They just type it into Excel or into a calculator like this, and the answer just pops out. The important thing in the real world is to understand what the standard deviation means. It's not to be able to calculate it. It's cool to be able to calculate it. I like the feeling of knowing I don't have to have a machine tell me what to do. I think it's kind of neat to be able to use the formula, but I'm not doing it. I'm going to do it once in my life and just be like happy that I can do it. And after that, I'm never doing it again. I'm not doing it unless somebody makes me. So we'll worry about the stuff. We'll worry about that rest of that later on. You don't need this, but what is that number telling you based on these symbols right here? The sum of those X values. Like, isn't that what you did to get the average? You added them all up, and I don't know if you wrote it down, but you got 391, then you divided by 5. So it's telling you what all of them are added up if you happen to want to know. And this is a little weird, but this is saying if you squared every one of the numbers and then added them up, you'd get this number. So we don't really need this one. And we really don't need the sum, since the only reason we ever have the sum is just to find this number anyway. So I really just need this number and then one of these two, depending on what the problem asks. Now I'm showing you this. You practice this by hand enough that you can show it to me on the test. But if you're like, I got this, then cheat on your homework. Like, just use this to get on your homework. You don't have to do that stuff by hand. You need to do it by hand a couple of times and then, practice it enough that you can show me on a test. But I'm showing you this for 2 reasons. One, because this is a terrible calculation and I'm not doing it unless I have to. And then secondly, you need to check your work. Like, notice this now tells me that I didn't blow it on all that previous stuff I typed in. So on a test, you should not get this wrong and not know it. I am going to ask you on a test, as I said, to do it by hand, but you should. How long did it take to actually type that once you're good at it? 20 seconds to type 5 numbers in and then do that calculation? Like, don't have the answer wrong. I'm going to wonder about you if you have the answer wrong on a test and you don't even know that it's wrong. Tell me it's wrong and say you don't know why. The right answer is this. The right answer is 12.859. Somehow I got this answer. I don't know what I did wrong up here. Like, see, the cool thing is if that's you in the real world, then all you have to do is phone a friend, say, hey, what's going on? I made this calculation wrong. They'll straighten you out. Where you're dangerous in the real world is you get it wrong and you don't even know it. And then you publish your results and everybody dies or whatever. So it's like, you shouldn't get this wrong and not know it. You have a question, Shelley?
Q1 and Q3.
What's what?
Q1 and Q3.
Yeah, and that's what I want to tell you now, but because I don't want to overwhelm you, but that's something we're going to do next. I'll mention it now, but notice there's 5 numbers here: 65, 66.5, 72, 93, and 99. There's 5 numbers there. That's called a 5-number summary of the data. And notice it lists a couple things you do understand, which is the minimum, the median, and the maximum. You understand those 3, but what's Q1 and what's Q3? And we'll talk about that. And notice it also tells you n is 5. You should know that n is the number of numbers, and so that's 5. So notice it kind of tells you everything you need to know, plus some stuff you don't even know yet. Until you get the hang of this, like you might want to write some of that down, like write yourself a couple of notes. We're going to end up doing this a lot, even if you said, I'm determined not to memorize this. You probably will have to, just because of how many times you use this. But for a while, you're going to need some reminders, right? So just to kind of reiterate really quick, in the TI 84 or 83, actually, why don't you run through this one more time if I just give you some other random numbers? 16, 47, 83, 52. Go find these things. Find that and find this. So it was the stat button, and then first edit, and then second calculate, and you wanted one variable. That's where this was.
Is there a way to go back from the list instead of quitting and going back to the menu? Oh, okay.
Yeah. And so you could, in this case, just go type the numbers right over the top of the other numbers. You actually don't have to erase them. You could type right over the top of them. But this time, because I only gave you 4, does it make sense? You better delete the last one. Or you could put them in list 2 this time if you want to, but we won't need those other ones again. I would encourage you just to put everything in list 1 every time. Because remember when you went to one variable statistics, it wanted to look at list 1, and you won't have to think about that. So I'm going to go type these right over the top of the old numbers. Doesn't matter what order, 16, 47, 83, 52, and I'm going to delete the last one. Second quit. I might write that in here. Second quit. And then back to stat again. Except this time, one variable stats. I got 49.5, and I got approximately 27.4. You happy? Except that you're in that class and it's 81, of course. Happy? Okay. So I want to switch gears now a little bit. Where did that go? Right there. I want to switch gears and talk about this picture on your note sheet. And your note sheet is black and white, so this helps a little bit. But this is called, as this says at the top, the empirical rule. And this is rather remarkable. And again, I quickly said this going out the door yesterday. But stare at this distribution here for a second. Like, remember, what you're seeing here is not a curve. You're seeing a bar graph, and there's enough bars that the bars kind of end up looking like this. So you have to see this as like there's a bar here and a bar there and a bar here. What shape is that distribution in? What do we call that? Yeah, that's normal or bell shaped. It's not pushed to the left, pushed right. It's a bell shape. And this is kind of what happens in lots and lots of places. So if we were to check your blood glucose level, we would have lots of people centered around. And what do you notice is a symbol right here. That's a little fuzzy. What's that symbol right there? Look at your note sheet at the bottom. What's that? What's that? It's this Greek letter pronounced mu. Again, it's annoying that they use Greek letters in some respects because we don't speak that, right? What was that? What's that the symbol of again? That's the mean. So it's just another way to say the mean. So basically, if we took people's blood glucose levels in this class, most of us would have numbers that were around the mean. Does that make sense? Now, none of us know what the right answer to that question is. So if I took my blood glucose level, I wouldn't even know what to make of that, right? I wouldn't. I was like, is that good? Bad? I wouldn't know. I'd be waiting for the doctor to tell me, oh, you're fine, and I'd go, okay, great. But how did the doctor know that? How does anybody know that kind of stuff? Well, you have to go take a bunch of data. There's not a right mathematical answer to what your blood glucose level should be. It's just you check living humans and see what they are. And so does it make sense? Most people would be structured around the mean, and then it would be less and less likely to be really far away from that, either high or low. That shape happens a lot in the real world. Now it turns out, and what do you notice about, what's this say right here? Can you interpret that hieroglyphics right there? Yeah, if you take the mean, and didn't we just do this a minute ago with those scores? If you take the mean and you add 1 standard deviation to it, that's the line right there. Notice this doesn't even specify what you're talking about. This is for everything. This is for blood glucose level. It's for the heights of women in China. Like, it's for shoe sizes. It's for everything. If you take any data that you collect and you made a bar graph of it, and that bar graph is basically bell-shaped like this, roughly bell-shaped, then this principle applies. So if you took the mean and you added 1 standard deviation to it, and you took the mean and you subtracted 1 standard deviation of it, that would capture 68% of people. So does it make sense if your blood glucose level was in there, the doctor would say, get out of here, you're doing great, right? Now, if that's true, 68%, there's still how many other percent of people walking out there that didn't make it into the middle? 100% minus 68% is 32%. That's still a lot of people, right? So you're not dying. If you're not in that group, you're not dead. That's a third of people. Now, isn't this what we just did a second ago? So we did this, right? We said we took our mean of 78.2 and our standard deviation of 12.9, and I added one to it to get this number, and I subtracted 1. And so this is a lazy person's way of saying it, plus or minus. I didn't have to write it twice. I subtracted 12.9 and I got this number. And so what we're saying here is that captured 68, that captures approximately 68% of people that took the test are going to fall inside that range. But remember, that means 32%. Still lots of people fall outside that range. If you jump out 2 standard deviations from the mean plus or minus 2 of those, that captures 95%. Isn't that what this note is saying right here? 95%. If you go mean plus 2 standard deviations to get to the high side, and then you go mean minus 2 standard deviations to get to the low side, that captures 95% of people. Now that you mostly captured everybody. Does that make sense? So if your blood glucose level is outside of that, now they're looking at you. Does that make sense? Does it mean you're going to die? Not necessarily. 5%, that still didn't capture 5% of people. And remember, 5% is a decimal. 5, you should be able to do this in your head. 5, perfect. 5%. That's what 5% is, right? And if I divide by 5, I get 1. If I divide by 5, I get 20. 5% is still 1 out of 20 people. That's still quite a few people. I mean, In a room this size, that's one of us. One of us is outside that range. So it's not like if you're outside there, you're gonna die. Or, you know, you're weird, you're crazy. What's the word that I put on my paper a minute ago? Unusual. That's unusual. Is it crazy? Is it extreme? No, but it's unusual. So the doctor basically is not gonna like put medication on you. They're gonna say, why don't you come back in a couple of months? Like do these two things, come back in a couple of months and let's see if you're now inside the usual range, and then they're gonna high five you and then you're on your way. But if you stay out there or you get a little worse, well, now it's time to do something. You see how this is decision making? This is not nerds with nothing to do. This is how you decide if somebody's doing okay. You need the mean and you need the standard deviation. And this empirical rule is amazing for that reason. Now, you may wonder a little bit, and I'm going to show you just a hair of this, but you may wonder, like, how did somebody come up with those numbers? Like 68%, 95%, where did that come from? Well, it turns out that's actually that's something calculus gave us. So if you took algebra 1 in high school, algebra 2, and then pre-calculus, then finally you'd be taking calculus. That's really hard. Like the math that created that is hard. It is beyond us. But when I teach calculus, I actually show this as an example, like an application. This is one thing calculus does that actually makes the world a little bit better of a place. So you do need to understand it's like practically what makes this kind of cool is, does it make sense this is how you should order shoe sizes? So if you're a shoe manufacturer, do you just make the same number of every single size? No, you need to know what the average shoe size is for, and by the way, it'd probably be different for every country, wouldn't it? But it's like you need to know what the average shoe size is for, say, let's say you're ordering women's shoes, and you need to make sure that 68% of them are within one standard deviation of the mean, because you're hoping to sell them all, right? Like that's what the shoe sale rack always has, the giant and tiny shoes on it that people didn't need. So any shoe you don't sell, you just lost money on. So does it make sense? The practical side of this is order 68% of your shoe sizes within one standard deviation of the mean. Now, what's kind of cool about this though is notice I broke it down. Does it make sense this? And so you're going to need this sheet for lots of things, but if you go right down the center of this, if 68% is within one standard deviation, if you cut that in half, does it make sense? Half of 68 is 34%. So if that's true, then can you figure this out yourself? Think about this for a second. Why is that 13.5? So this little area right here, just that pink area is 13.5. Can you punch calculator buttons and figure out where they got that? Given that the entire area from here to here is 95. Some of you are better at this kind of thing than others. What calculator buttons do you push? Would you push to get 13.5 there? How'd they get that? Yeah. There's more than one way to do it, but one way would be to, well, say, if 95 is all the way from here to here, then couldn't you cut 95 in half to get this pink plus blue? And then if you took 34 away from that, then that would leave this number behind. Like you could figure this out for yourself. You don't have to be looking at the sheet. Or you could say, I'll take 95 minus 68. Does it make sense? 95 minus 68 would give me all of the pink, both pink areas. So when you do that, 95 minus 68, you get 27. And then if you cut 27 in half, you get 13.5. So I heard some of that. So you will have this note sheet, so you don't have to figure that out yourself on a test. So I'm going to add this because I want this to get into your brain. This is usual. If you're out here, now you're unusual. mean, those are words. So if your glucose level was clear over here, then the doctor would say, cancel whatever else you're doing today. You're going into surgery right now. Does that make sense? If you're right here, what's the doctor going to say? Does it make sense you're out there in the unusual, but you're not very far into it? This would be like, go do some things different and come see me in a couple of weeks. Like, we got to do something about this. So do you understand that's just somebody saying, why don't we make the line here? There's not a mathematical reason for this. It does sort of feel like 95, if you're in the middle, 95% of people, that's pretty typical, but 1 out of 20 is still some people. So it kind of matters where you are. If you're not in the usual area where we kind of don't have to worry about you, everything is fine medically, it's kind of a question of like, well, how far out there are you? Well, look at these other percentages. If you're in that yellow area, that's only 2% of people that made it into that yellow area. That's not very many people, but 2% is still 2 out of 100. It's still 1 out of 50. But if you start getting out here, notice that's not 15%, that's 0.15%. If you start getting out there, now we got to start moving. We got to move on that. That's a, you know, and it could just be shoe size. Like, that's not a medical problem. It's just like, man, your feet are huge. That's really cool. Sometimes it doesn't matter. Other times it's something medical and it does matter. If you're actually out here, we'll talk about this in a couple of sections, but now you move from what statisticians call unusual to an outlier. Like, now you're an outlier. That's where it's kind of like, that's really strange now. Like this, and sometimes that's really good, right? Like, how much money do you make? You're an outlier high. That'd be great to be an outlier. But if that's cholesterol, man, it's not so great. So you're not just different. You're not just unusual from other people. You're extremely different than other people in that regard. Did you see why this is kind of a powerful device? And all you have to know is the mean and the standard deviation, and then what your score is to kind of figure out where you are here. Isn't that kind of cool? That's what we've got to look at. Notice there's one more percentage on here, and maybe you can see why I called that an outlier. If you go out to 3 standard deviations, we need a new color. Let's go blue. If you go out to 3 standard deviations in either direction, notice how many people that captures. 99.7. That's pretty much got everybody now. Does that make sense? 0.3% are left over. And if you divide 0.3% in half, you get 0.15%. Do you see where that came from? And so if you're outside that, you're an outlier. That's not just unusual. That's an outlier. This is like, let's go to surgery right now. So these are percents that lots of teachers would say you should memorize, but I'm not saying that. Like, you got this note sheet. Okay. So let's switch gears for just a second here. What am I doing? Stop. You don't need to know this, but I just think it's kind of cool, so I'm going to show it to you. What's going on? I hit Google. How come I'm not getting any Google? So I'm going to go into an online graphing calculator right now because it's actually better than your graphing calculator. Man, I don't see that I have this written down. So it turns out that bell-shaped curve, if you've taken a little bit of algebra, maybe you know that equations have shapes. And I think it was Hannah the other day that said that that curve kind of looks like a parabola. So she's taking a little bit of algebra. Like, there's equations that model different curves. Now, because this is just kind of good this is good practice rather than me, like I don't have it written down in my notes, which is sort of stupid because I want to show it to you, but I don't have it memorized. And I about have it memorized, but I'm going to ask this, what is the equation for the bell-shaped curve? So I'm just looking for, maybe I'll go to images. So there it is. Notice that is a really crazy equation. So it says 1 over, you recognize that number, you recognize that symbol. Notice that's the standard deviation. And then it's the square root of 2 pi. And then there's this e, which most of you haven't studied. And then it's raised to this crazy exponent. And so to keep this really simple, I'm going to make the mean 0 so that the graph will be centered at the XY axis, if you know anything about that. And then I'm going to make the standard deviation 1. Notice the standard deviation shows up here and here. So I'm going to type that into this graphing calculator. I'm probably going to get this wrong. I'm going to have to go back and do it again, but it was 1 divided by the square root of 2. Again, you don't need to know this, but I just think it's neat. It's kind of interesting. And then it was e raised to the, oh dang, I think it was x, I think it was 1/2 x squared. Was that it? X squared. Notice the answer is no. Does that look like a bell-shaped curve? So it's like I missed something, right? X squared divided by 2. Oh, there's a negative in front of it. See that negative right there? I forgot the negative. Aha. Now to make this look a little easier to see, first of all, notice the bell-shaped curve goes forever. That's interesting. It actually goes forever in both directions. So it turns out that the reason we know that 68% and 95% and so forth is because some nerd figured out an equation that actually modeled that. And I say some nerd because like those are my people, but I didn't do it. I don't know how to do that. I don't know how somebody figured that out. That's a really crazy equation right there. But watch this. So I'm going to do some calculus now. In calculus, there's something called an integral. So if I say I want to go from -1 standard deviation, so that's over here, from -1 up to +1, and I would like, and this symbol means sum, which means find the area under that curve. That would mean something to somebody in calculus, and I'm basically saying do that for this graph right here. What do you notice it says the answer to that is? What's the area under that curve? 68%. Now notice it's actually not 68%. It's not perfectly 68. Interestingly, it's at 68.268949%, but we don't, 68 is close enough, right? We're just doing this to kind of get the idea. So isn't that kind of cool? Notice what's interesting about this curve is the area under it is always 100%. It's 1. The area under this curve is always 1. And so that's 68% of it. So you tell me, if I go out from -2 up to +2, what am I going to get? In other words, 2 standard deviations below. Isn't that where we got 95 a second ago? Again, notice, is it exactly 95? No, the 95 is close enough. Now you look at your note sheet. What if I did this? What if I went from negative, I'm not going to do this so you can't see it yet, but what if I went from -1 up to +2? Because you're going to have assignment questions like this. Can you look at your note sheet and add up the percentages? If I went from -1, 1 standard deviation below, up to 2 standard deviations above, what am I going to get? Notice the exact answer to that is roughly 82%. Is that what you got from your sheet? So basically, I could find the area under this curve from anywhere. Let's do the -3 up to +3. Isn't that 99.7 on your sheet? See where they got 99.7? It's actually not 99.7, it's 99.73, but you know, close enough, right? So it's actually calculus, it's math that gave us those percentages. But that's kind of cool that, I mean, like, we don't have to understand that. We can take what they learned. That's cool that they learned and they know that. But I'm also showing you this because that's why there is a reason for some people to keep taking a bunch of math. It actually does come out in the sun and actually help people do things. Calculus is the reason we know how to calculate beams for houses and bridges and so forth. So, you know, the fact that somebody understood that, like, it does pay off. It isn't always just nerds with nothing better to do. So part of the reason I showed you that is just to motivate a little bit of study. Bring that sheet with me. Okay, so I want to share this screen one more time and have you look at something else here. So what you're going to be asked in your assignment is to use these percentages. And I'd like you to kind of practice that a little bit right now for the sake of your assignment. It's not just going to say, you know, what percent are between 1 and -1 standard deviations, and then you go, oh, look, it's 68%. It's going to ask you questions that make you think a little bit harder than that. And I think I actually made copies of this, but I think I managed to leave them in my office, but I think I can bring them up here. I hope I can. Yes, right there. So I'd like you to see if you can answer these questions. So I reproduced this on the sheet for you to practice and reminded you what's on the note sheet, which you don't need to know. And this is something I want to go in your head, but it's always 100% total underneath that curve. However, to get that, you actually have to go forever. You can't ever stop. But if you never stop, it'll always be 100%. And then I just reminded you on this sheet that mu is the mean and sigma is the population standard deviation. So take a look at that first question right there. So in America, I looked this up, mother's birth age 2020, let's say that's 30. Notice I said mu is 30, which means that's the population standard deviation when mothers gave birth, it was 30 years old. So again, that must mean that there were 27, 28-year-olds, but then also 32 and 33-year-olds, right? But the standard deviation was 4. In other words, and again, I would ask you, could you explain if I put that on the test, what does that mean? Like, what does the standard deviation mean? You will not pass this class if you don't at some point get a working knowledge of standard deviation. What does that mean? It means it was very typical for, although 30 was the average, it was very typical for people to vary from that by 4. In other words, it wasn't weird at all to be 34 or 4 minus that 26. And what we just learned is 68% of people then would be in that range from 26 to 34. So it's actually, notice, and this is a great example because notice we don't have the original data. Some nerd already did it. Like, this is like you Google search and said, what's the average age of a birth mom? And you got the answer to that question, but we don't have the data anymore. It's gone. We just have this solution from the data. So I asked the question, find the percent of mothers older than 26. We can get that entirely from nothing else. We can actually get that just from this empirical rule graph alone. But you have to say, oh, 30 minus 1 standard deviation is 26. So where does that put me on the graph then? Do you know, like, where are you on the graph? Do you agree this is the average? So that's the 30-year-olds, correct? And we went 1 standard deviation below that. And so 26 is right here. Do you agree with that? And so what did this question ask? Find the percent of mothers older than 26. So since we're here, then it's like find all of these percentages added together. Does that make sense? Now, the hard way is to say, okay, 34 plus 34 plus 13.55 plus 2.35 plus 0.15. But what's this right here without even adding it up? All of that. That's the right half of the graph. And so since the area under this graph is always 100%, then does it make sense that right half right there is already 50%? Like I don't have to add it up. Now, if you got nothing better to do and you want to add it all up, knock yourself out. And so does it make sense 50% plus 34%, that'd be what, 84%? Now, what you need to understand is how powerful that is. That means if you're a pediatrician, that you could sort of predict, not report on what happened yesterday, but actually predict that in your practice, 84% of the mothers that come in will be older than 26. And maybe that matters. Like that just sounds like curiosity to me, but maybe a better question would be, maybe we will figure this out. What if I said what percent would be older than 38? Why might a doctor want to actually know that? Yeah, if you get to a certain age, it starts to be a risk to the baby and the mother. And so if you could predict, not again report on the past, but actually predict what percent of your mothers that came in to have kids would be older than 38. If you knew what percent that was, and that kind of meant you better be ready with some medical interventions for those patients, then it kind of might be like, wow, we need to know something about this. Let's take the time to do this all the way through. So 38, what's 38? What do you do to 30 and 4 to get yourself to 38? Blurt it out. How many standard deviations are you above? 2 of them, right? You got to take 30 and add 2 4s to get to that. So doesn't that put me here? And we said, again, older. So I'm adding these 2 percentages together. So I get 2.5%. Now notice there's another way to look at that because added these 2. So this was mean plus 2 standard deviations. That's where a 38-year-old would be on this list. And so we said older. So that'd be the yellow plus the black. So that's 2.5%. Or you could say, I could have figured that out myself because if I knew 95% was from here to here, from here to here, then I could say that leaves 5% outside of that, and I'd have to split that from the top and the bottom tail. So you could have figured out that was 2.5%, reasoning it out yourself as well.
You're adding all of the other ones? Plus this?
Yeah, so I'm basically adding these 2 together, 2.35%, because it was said older than 38. So that means this way. So that's 2.35% and 0.15%. So I got 2.5%. You agree with that? Now, again, why is this practical? Well, what if you do this on your calculator? First of all, what's 2.5% as a decimal? Type this in. What if you had 1,138 patients at your pediatric hospital that year? I don't know if that's realistic. Maybe it depends on the town you're in, right? What if you had 1,138 patients? So you might say, well, 2.5%, that's really small. That's not that likely to happen. But if you have 1,138 patients every year that have babies, again, this is why we practiced percentages. What do I do to figure out 2.5% of 1138? Don't I change 2.5% to a decimal? That's not 20, that's not 0.25. And of means multiply. Like, this is the kind of thing you need to be able to do to make this practical. These are the kind of questions that you would see on a test at some point. So if I take 0.025 times 1138, whoa, that's approximately 28 patients. So if that like takes some special machinery, some special medication, does it make sense you could order for the year and actually predict that you're going to have 28 patients? Now, does that mean you'll have exactly 28? No, there's variation. Some years it might be up, some years it might be down. This is just a prediction. But you see, that's kind of cool. You can actually prepare. Like, you should have known this. That's the idea. If you're the mom and you come in there and they're not prepared, it's like, dude, didn't anybody in this institution take statistics? You should have known this. It's predicting the future. That's what makes statistics powerful. It's not just nerds trying to report on what happened yesterday. You understand that? This is the decision. This is decision making. Can you see how if you were the person at the hospital that could actually tell this, you could actually go online and look up the mean is 30 and the standard deviation is 4 and make a calculation like this? How many patients did you have here? 1138. It's like, yeah, you can actually predict you're going to have 28 patients. Can you see how it's like, man, I better give that person a raise. I better give that person more responsibility. It's like, isn't that what you're doing in this class? But the question is that how you're learning this stuff? Are you just poking buttons in your assignment to try to get it over with? Or are you, this is hard. Like, being good enough at this that you can actually do something takes some thought. But it's like, you got to know percentages. You got to understand what a mean is, what a standard deviation is. It's like, we're only 2 weeks into this class. Like, this is pretty cool. Like, you can already do some pretty neat things. But again, just watching me do it once, because I practiced this a lot of times, is not the same as you understanding it. But my point is, think, ask a lot of questions, reason about this, try to get to where you can actually do something. Okay, so you do these two. Find the percent. That's all you're doing is finding a percent, but find the percent of mothers younger than 22. And again, you might say, yeah, if they're younger than 22, maybe that is something we'd have to be cautious with as well. Maybe if they're too young, that's a little dangerous. And what about C? Find the percent of mothers between the ages of 22 and 34. Like, these are all predictable things. Can you find those using your note sheet? Again, I'm not assuming you can do this. That's where we're practicing. So ask a question. What about? Call me. I can print you one. I think the day you missed is the day I handed them out. So it is. I'll print you one before we leave. I think I have to get out of this to print, and I don't want to make that go away for other people. But yeah, we need to get you a copy. No, I'll print you one before you leave. It prints in that next room. So. So the key would really be to do this. See what you got. If you say the mean is 30 and you added 4 to it, then this would be 34. If you added to it, that'd be 30 added 4. I'm adding standard deviations, right? So 30 to 34 to 38. And if I add 4 more, this would be 42. So notice this would indicate that 0.15% of mothers are more than 42 years old. If I go the other way and take 4 away, 30 minus 4, 26 minus 4, there's 22. 22 minus 4 would be 18. So now when these questions say, what percent of mothers are younger than 22? Notice I can say, there's 22. And so what percent is that way? 2.35 plus 0.15. That's the same answer we had a minute ago. That's 2.5%. Again, that would mean in this particular hospital, that'd be 28 patients that would be young mothers, so to speak. 22 makes them young. What percent of mothers would be between 22 and 34? Well, do you see that as here's 22 and here's 34? So I need to add everything from here to here. Oops, went to the wrong spot, didn't I? 34 is right there. So I've got 34 and 34 and 13.5. So 68 and 13.5, what is that, 81.5? Did you get 81.5? Now, we'll get here later, but what if somebody wanted to ask the question, what percent of mothers are, say, more than 40? Does it make sense the only numbers we know are like these, it's like 30 and 26 and 38? What if somebody said, what percent of mothers are over 45? Does it make sense we don't have, you can actually answer all those questions too. So we'll talk about that a little bit later. There's some buttons on your calculator, so you can actually answer any question you want. You don't have to just stick with 4s above and below the average here. But you can appreciate right now that if you can't do it here, where we're landing on nice locations, then it's going to be really hard later on. So you got to make sense of that. So stare at this one. A little bit harder because baby weights, the mean baby weight, 7.5 pounds. I found that on the internet. The standard deviation is 1.2 pounds. Very typical to deviate by 1.2 pounds up and down from that, and not even, and very even usual to vary by 2 of those. So could you find the percent of babies born weighing more than 8.7? Maybe that's like dangerously high. That doesn't seem dangerously high. Find the percent of babies born weighing less than 5.1. That seems dangerously low, like being in the NICU, right? Neonatal intensive care unit. Or what percent are born weighing between this? Remember, we're predicting the future. That's what's so amazing about this. So I'm going to shut up long enough for you to calculate every one of those. Notice totally different context, yet same exact empirical rule works for this too. Does it make sense babies would be born in a bell-shaped curve? Most of them would be stacked around the middle, 7.5, and then they disperse out from there. See that long enough? You get a copy of that? Yes. No, that's identical. That's exactly the same thing that's up there.
No, I'm saying that you must have the question.
Correct. I printed this out. I meant to bring it, but I just ran out the door and sitting up in my office. So
Yeah, no.
can you see that okay? So if I zoom in on this, that's probably helpful, but you can't see the chart. So if you don't have your note sheet, look at somebody else's, pull up my open math. I'm going to shut up here in just a couple of minutes as we answer this, and then let you ask me questions about Excel and about. Good. Okay, so that first one says percent born weighing more than 8.7. So the first thing we got to do is kind of establish what's that mean. In the middle, question up there says what percent of babies. This is an example of something I would give on a test right here that would kind of demonstrate that you understand this empirical rule. So you don't need to, you're not turning this in, but you need to be able to do this. Left over from this. Justin, copy of this? Okay, I'm going to catch up to you and then we'll be. Here's what you ought to do, in my opinion. You can use this up here and kind of write right on top of it, but I'm just going to make my own. So we were told the average was 7.5, and of course that would be the middle, right? Because that's where most people are. That's why it's the average. But then if you go up 1.2, that's the typical standard deviation. So if I take 7.5 and I go up 1.2, 7.5 plus 1.2 is 8.7. 8.7 plus another 1.2 would be 9.9. Does it make sense? I have 1 and 2 standard deviations labeled now above it. Now, if I go below it and do the same thing, if I go down 1.2 from 7.5, that gets me at 6.3. And if I go down another 1.2, that gets me down at 5.1. And so I have plus or minus 1 and 2 standard deviations labeled. Maybe I need more, but doesn't that give me the ability to answer this first question? More than 8.7? What percent of babies are born more than 8.7? Well, wouldn't that be then from here on? So notice this was 1 standard deviation, this was 2. So 1 standard deviation, that was right here. Now again, watch this, no matter what happened to you here, watch this, because there's an easy way and a hard way. The hard way is to add 13.55, 2.35, and 0.15. What's the easy way to get these all added up? Good job. Isn't this entire right side from here 50%? So if that much of it's 34, then couldn't I just go 50 minus 34? Again, this isn't a race, but I can see that the answer to that is 16%, whereas if I had to add these, I'd have to bust out my calculator, and that's fine. It's not that much faster. So, did you get 16% for that one? What about weighing less than 5.1? Well, that would be this. And remember, that goes forever. And this is minus 1 standard deviation, minus 2. So what percent is below minus 2? So that's right here. Notice it says minus 2 right there. So hey, that's the same answer we got a minute ago. It's 2.35 plus 0.15. That's 2.5%. So again, if you're a mom and your baby's born 5.1 pounds, then it's kind of like, wow, that's really, that's on the edge of being unusually small, right? Is it dangerously small? Is it outlier small? No, it's not 3 standard deviations below the mean. That's an outlier, but it's unusual. That's unusually small. And then between 3.9 and 7.5, let's see what's between 3.9 and 7.5. Hey, look, 7.5 is on here, but notice 3.9 is not. Well, that's because I didn't go down one more step. 5.1 minus 1.2 does put me at 3.9. So this is saying what's between here. What percent is that? So that's between 0 and -3 standard deviations. So that's from here all the way up to here. So I'm adding 34, and I think that was 13.55 and 2.235. Like I'm adding all those up. Which would be easier though, if I had, instead of adding those, since this is all that didn't get included on that side, I could just say 50% minus 0.15%. You got to be careful with that though. That's not 50 minus 15. It's 50 minus 0.15, which is actually 49.85. So the power of this is in predicting the future and the fact that it works in every circumstance. It works for mothers' birth ages. It works for baby weights. It works for shoe sizes. This is pretty powerful predictive tool. That's what's so cool about this. So you'll see a number of your questions in your assignment. Okay, so I want to give you a little time to leave because you're fine, or you owe me, I think, due Friday? Is the Excel due Friday? So your Excel's due Friday, so you might have some questions about that, or perhaps something in my open math. So you have the rest of this time to do whatever you want. Oh, sweet. Thank you. That's probably Andrea. What did Andrea say? Thanks for noticing that. Yeah, so if you're still listening, Andrea, if you look in my open math, there is a lab, and I don't know if you were in the class when we started that. Were you in here Monday? Monday in classes when we talked about it, and I don't think I recorded that, but I will go pull that up.